Hey guys, so we're going to start chapter 7 with some simple conceptual stuff, a chemical versus a physical change. There's a couple of pieces to this chapter that I'm going to grab from chapter 8 as well, and when we get to that part, I'll let you know what's going on. Won't be much of a big deal because we're going to slide into chapter 8 from chapter 7 anyway. They saved a few reactions to go over out there, and I think it would be nice if we just presented all of the reaction types up front. But starting out with just some simple, what is the difference between a chemical change and a physical change? I think most of you guys have some pretty good ideas already in your head about that kind of stuff. Sometimes it can be a little confusing. Some people might say, for example, think burning wood is simply just a physical change. It's actually a chemical change. But I think for the most part, most of us understand the difference. Something that's physically changing is simply just changing its physical state. So what that means is we're going to have to focus on what are the physical states again. Well, in this class, we talked mostly about solids, liquids, and gases. There are other physical states. Plasmas exist, for example. But if you take water, something as simple as that, if I were to take an ice cube and melt it, I take solid water. So I'm going to write these out for you here just as examples. So I'm going to take some solid water, as in ice, and this little S down here means that that particular molecule is in the solid state. We're going to melt this thing, so you're going to have to apply some heat. We have a symbol for that. It's a little delta. And that little delta can mean a bunch of other things, and we'll go through what goes above and below the reaction arrow, what that reaction arrow actually means in a sec. But we're going to take that solid water or that ice, and we're going to allow heat to come into that system, and it's going to turn into a liquid. So what you haven't done is you haven't changed the water molecule. It's still H2O. You haven't taken an H off of an O or anything like that. It's literally the same molecule, just in a different physical state. So as long as you haven't changed the molecule itself, or the actual structure of the species itself, all you did was change the physical state of the species, then your particular molecule has simply undergone a physical change. How about a chemical change? Well, there's a pile of examples, right? And we can all do all kinds of chemistry. Metabolism is a pretty good example of a chemical change. You're going to take food and you're going to sort of chemically break it down, and your body is going to get energy out of it, right? Plants make glucose and oxygen from carbon dioxide and water. And the reaction that we can write for that is we're going to take some carbon dioxide. So this is where you guys are going to have to know how to draw your covalent molecules and your ionic compounds just from the name. Applying the physical state in this particular case might not be super necessary, but I'll put it in there anyway. Sometimes it's actually crucial to say the problem you're trying to solve or whatever calculation you're trying to do. You have to know what the physical state of the species is. But for right now, I'm just going to write out all the major players here. So we've got carbon dioxide and we've got water that the plants are going to take in. And the water can be in the liquid phase. That's fine. We're going to take a little light, right? So photosynthesis requires a little light. H nu is our little symbol for that. Remember that from, chapter 2. And they're going to make glucose, so C6H12O6. And that will probably be in the aqueous phase, right? So that's the sugar solution that goes up and down the trees. It goes up and down, the stems and out into the leaves and all that stuff. So that's the food for the plant, right? And aqueous, that little AQ, means that sugar is actually dissolved in water. Aqueous means that the water is the solvent, and the molecule right before the little AQ that we've written down, that glucose, is the solute. So Oxygen is also a byproduct of this reaction, and that'll be in the gas phase. This is why we love plants. And if anybody's paying attention to what happened here in this chemical change, you'd notice that this reaction is not balanced. That's another piece of chapter 7 that we're going to go over together, how to balance chemical reaction equations. So right now on the left side of the reaction arrow, we have carbon dioxide and water. And so on the left side, if you were to total up all the moles of carbon atoms, you would see there's 1, right? You see 1 C over there. But over on the right, you see there are 6. So we're going to go ahead and balance the reaction equation. We notice that on one side we have 2 hydrogens, and on the product side, which is on the right-hand side, we have 12 hydrogens. We notice on the reactant side of the equation, we have 3 moles of oxygen atoms. And over on the product side, on the right-hand side of the reaction equation, you'll see that glucose has 6 and oxygen has 2, so there's 8. So I'm going to go through how to balance an actual chemical reaction equation with you guys. For now, I'm just going to go ahead and balance this thing so that we can move on. So we'll put a 6 in front of carbon dioxide and a 6 in front of the water. And on the product side, we're going to put a 6 in front of the oxygen. So we'll go through sort of the how-to. There's some reactions. There are some reactions that are easier to balance than others. Some of them are pretty straightforward. There's a pretty easy little trick that we can use to keep track of everything. But for now, that's basically an example of a chemical change. And we're going to go through all this stuff as we move through Chapter 7 and take some pieces of Chapter 8. We're going to start talking about chemical equations and the different types of reaction equations that there are. So for one thing, we can talk about all this stuff all day long just using words. For us in chemistry, it's often easier to write down a reaction equation, keep everything simple, right at the top of the page. It's kind of like reading a recipe, but instead of all those words, or instead of seeing a picture of a cake, right, you can actually write out the molecular structure of either your covalent molecule or your ionic compound. For all the reactants that are coming in to, join together, and we'll draw a specific type of an arrow, and on the right-hand side of the arrow, you have all of your products. So that way you would see the picture of your cake over there, or your cookies, or whatever the heck you were making. So for us, we're going to write out some chemical equations, and by convention, we will put the reactants on the left-hand side of the reaction arrow, and the products are going to be written on the right-hand side of the reaction equation. So instead of saying this equals that, so we went through in chapter 1 all the laws of definite proportions and the law of conservation of mass and all that stuff. Instead of taking the time to write an equal sign and then in words describing, hey, this is what happened on the left, this is what happened on the right, and look at how it all balances out, we're going to actually write a very specific type of arrow. So there are a bunch of different types of arrows. The one that I just showed you guys was simply reactants going to products. And so it was just an arrow that looked like that. Sometimes, and it depends on the area of chemistry you're working in organic chemistry, very often somebody will come up to us and say, hey man, I need 25 grams of this stuff. And they give you the product. So you draw out the structure of the product and you have to work backward to commercially available starting materials. You have to come up with the how to make that product by yourself as the chemist. The arrow that we use to go backwards, but still drawing the conventional reaction equation with reactants on the left and products on the right, is this kind of an arrow. You won't see this very often in this class, but if you do see this, that is our retrosynthetic arrow. That tells you that whatever is written on the left, still your reactants, whatever's written on the right, still your products, but somebody's asking you to work backward. They're telling you, hey, I need, 5 grams of this amino acid, go to town. You have until Thursday, that kind of a thing. So then you're going to draw that arrow and you're going to strategically break bonds, right, every step of the way until you get backward to the left-hand side of that arrow where your reactants actually hang out, whatever you can buy, and get started. Sometimes you'll see an arrow that has one piece, like that single head, right, pointing toward product. And then sometimes right underneath it, you'll see another half of an arrow with the single head pointing toward the reactants. And this is a very special kind of an arrow. So this is either telling you that your reaction is reversible or that your reaction is in equilibrium, meaning the rate at which you convert your reactants into products equals the rate at which you can convert your products back into reactants. So there are a lot of things that achieve dynamic equilibrium. So equilibrium is a dynamic thing, right? So it's not like the reaction has ever stopped. It's simply like, okay, I'm going to take some nitrogen and hydrogen and I'm going to allow them to come together and make some ammonia. But then at the same time, once that happens, there's this backward reaction. Hey, the ammonia can decompose and work backward and make nitrogen and hydrogen gases again. So we draw this arrow to let someone know this reaction is in equilibrium. Sometimes when your reaction's at equilibrium or has achieved equilibrium, you favor the products over the reactants. And so we'll write something like that. Sometimes, and if you're the chemist, this totally sucks, you actually favor the reactants over the products at equilibrium. And then if you want those products, you've got to figure out a way to push that equilibrium over to favor the products. And there's a bunch of different ways that we can actually do that. In Chem 32, we spend an entire chapter talking about equilibrium and how you can affect it. All right, so, and then there's this one last arrow, and I might as well show you because I might put it in on occasion. You'll see this a little bit more in organic chemistry, but this one would probably be sort of like hanging out underneath the reaction arrow, and it'd be something like this. That simply just means that your reaction is refluxing. So you've done something to your apparatus to keep the solvent from evaporating, right? You've put some sort of, condenser tube on top where you're going to fill it with cold water, and the vapors from your solvent are going to go up and hit that cold outside of the water jacket, and they're going to come back down and drip into your solution. Kind of like when you get acid reflux in your stomach, right? So acid vapors are sort of, the gas, right, is sort of coming up, your esophagus and burning, that feeling, and then dripping back down into your stomach. So that little weird looking arrow sometimes we use just to let someone know that our reaction is refluxing. But